US Physics Olympiad, year 2020, F equal MA. First round, exam B. As usual, it was given 75 minutes for 25 problems. Problem number 1. A ball is bouncing vertically between the floor and the ceiling, which are both horizontal and separated by 4 meters. All collisions are perfectly elastic, and when the ball hits the floor, it has a speed of 12 meters per second. How long does a complete up-down cycle take? Solution for problem number 1. First, let's write kinematic equation for ball motion. We have height h equal 4 meters equal initial speed v, which is 12 meters per second, multiplied by time to travel to the ceiling, minus 1/2 gt square. So we need to solve this quadratic equation to time t. That will be 5t square minus 12t plus 4 equals 0. We have two roots. One root with a negative sign here is our solution, because in that case ball is going up till the ceiling, and the positive sign here is responsible for motion of this ball up to ceiling, up to highest point, and down to ceiling, which is not our case. So that will be exactly 1/2 of total time, because due to symmetry it takes the same time to go from ceiling to the floor. So finally we have total time equal 2t or 0.8 seconds, which is answer D, and that was solution for problem number 1. Problem number 2. A uniform rod of mass m and the length L has moment of inertia ml square over 12 about an axis that is perpendicular to the rod and passes through its center. What is the moment of inertia of a uniform square plate with mass m and the side length L about the axis along its diagonal? Solution for problem number 2. Let's place the origin at the center of mass of the square. The perpendicular axis theorem states that for a two-dimensional mass distribution in the xy plane, we have Iz equal Ix plus Iy. If the x and y axes are oriented parallel to the square's sides, then the moments of inertia Ix and Iy are both those of the uniform rod of mass m and length L. So we have Ix equal Iy equal ml square over 12. This implies Iz equal ml square over 6. Now consider rotating this axis by 45 degrees about the z-axis, giving axis x prime and y prime along the diagonals of the square. The perpendicular axis theorem now gives us Ix prime equal Iy prime equal ml square over 12, where Ix prime is the desired answer. By symmetry, we have Ix prime equal Iy prime equal ml square over 12. So that's the answer A, and that was solution for problem number 2. Problem number 3. A conical pendulum of length d swings in a horizontal circle of radius small r as shown. If omega is the angular frequency of this motion, what is omega square? Solution for problem number 3. Let's write equation for this motion in vertical and horizontal direction. Suppose that tension in this pendulum is T. In vertical direction we have equation t multiplied by cosine theta equal mg, where angle theta is angle between pendulum and the vertical. In horizontal direction we have tension multiplied by sine theta equal centripetal acceleration due to rotational motion, which is mr omega square. Now let's divide the second equation by first equation. We have omega square equal g tangent theta over r, but tangent theta equal r over square root from d square minus r square, which give us omega square equal g over square root from d square minus r square, which is answer D, and that was solution for problem number 3. Problem number 4. In 0G airplane rides, passengers can float around the cabin as if they were weightless. A flight trajectory for such a ride is shown below, with a few points during the journey labeled. Which of the following statements is correct? Take A to be the acceleration of the plane during the 0G part of the flight. Solution for problem number 4. The 0G segment corresponds to the part where the airplane falls freely with the passengers inside. That is, during the 0G segment, the acceleration is g downward, and hence a concave down parabola, corresponding to the segment from B to D. That was answer C, which is the 0G flight begins at B and ends at D, during which A equal G and A points down. That was solution for problem number 4. Problem number 5. A mote of dust is initially located at distance r from the Sun, which has mass big M. At this point the mote has a small tangential velocity v. Which of the following is a good approximation for the distance of closest subsequent approach between the mote and the Sun? Solution for problem number 5. Here we can use two expressions for total energy. From one hand, total energy equal potential energy plus kinetic energy, which is equal to 1/2 mv square minus g small m big M over r. This is for furthest point. But from other hand we have expression for total energy for elliptical orbit. That's equal to negative g multiplied by m small m big over a, where a is a big axis of the ellipse, which is smallest distance r prime plus furthest distance r. Now we can equalize these two expressions for total energy to each other, which is give us this formula, and we have this expression. Here this member and this member cancelled, and also because big R much greater than R prime, we have this inequality, so we can neglect this second member and rewrite full answer in form of r square plus v square over 2gm, which is answer C, and that was solution for problem number 5. Problem number 6. A three-legged table is shaped like a uniform equilateral triangle and has identical legs at each corner. When the mass of an object placed on the center of the table exceed m maximum, the table's legs will all simultaneously break. Which of the following shaded regions shows the area within which an object of 2m max over 3 can be placed without breaking any legs of the table. Solution for problem number 6. Due to symmetry, we have maximum mass which could be held by one leg is m maximum over 3. It means that if we put this mass 2m maximum over 3 in some point of triangle table, each force on each leg could not exceed m max over 3. Let's place our triangle and count all corners by letters A, B and C. Let's place our mass on distance y from base side BC, and the total height of triangle is h. So it means that we can write two equations for equilibrium. First equilibrium equation is Fa plus Fb plus Fc equal 2m max over 3. Second equation is equilibrium rotation about any axis. Let's take axis through our point mass parallel to base BC. Around this axis we can write equation for equilibrium. Fa multiplied by h minus y equal Fb plus Fc multiplied by y. Here, because axis going through our point mass, this point mass does not create any torque around this axis. Now we can write from last equation that Fb plus Fc equal Fa multiplied by h over y minus 1. And let's put this expression to our first equation. So we have Fa equal 2m maximum over 3 divided by h over y. And because Fa must be less than m maximum over 3, we can put this expression to this equation and find that we must have this inequality. And from this inequality we have h over y must be greater than 2 and y must be less than h over 2. So it means that mass must be placed on distance less than h over 2 from each side, BC, AB or AC. And this condition could be good if we choose answer A and place our mass inside of this shaded triangle. So correct answer is A, and that was solution for problem number 6. Problem number 7. Two satellites are initially in identical circular orbits around the Sun, with orbital speed v equal 10 power 4 meters per second. The first satellite fires its thrusters toward the Sun and quickly obtain a radial velocity delta Vr equal 1 meter per second. The second satellite instead fires its thruster behind it and quickly increases its tangential velocity by delta Vt. If the two satellites subsequently perform orbits with the same period, approximately what was delta Vt? Solution for problem number 7. By Kepler's third law, the period only depends on a semi-major axis A, because t square proportional to a cube. However, the total energy of an elliptical orbit is determined by the semi-major axis E equal negative gmm over 2a. Hence, the two satellites must have the same energy and hence the same final speed, because they have in this point the same potential energy. So we have V plus V delta V tangential square equal v square plus delta vr square. And from here we can count what is delta vt. That will be this expression, which is approximately this one, because delta vr much less than v. And finally, when we put numbers, we will get this much. So that's the answer A, and that was solution for problem number 7. Problem number 8. A conveyor belt is moving with the velocity v to the east. A block with velocity v to the south slides from the ground onto the conveyor belt. The coefficient of friction between the block and the belt is mu. The block stops slipping after a time. Next one. Solution for problem number 8. Relative velocity of the block compared to conveyor belt is square root from 2 multiplied by v. Acceleration due to friction equal mu g. Total time to stop for this block compared to belt is initial speed divided by acceleration, which is square root from 2v over mu g. That's answer C, and that was a solution for problem number 8. Problem number 9. Two equal masses m are connected by an elastic string that acts like an idle spring with the spring constant k and the unstretched length L. The two masses are hung over a frictionless pulley. What is the total length of the string at equilibrium? Diagram not necessarily to scale. Solution for problem number 9. Balancing the string tension with the gravitational force on either of the masses give us kx equal mg, where x is enlargement. From here we can find that total length of this string in equilibrium equal L plus x, which is L plus mg over k. That was answer B, and that was solution for problem number 9. Problem number 10. The two masses are both displaced downward by a small vertical distance x and simultaneously released from rest. What is the period of oscillations? Solution for problem number 10. Gravity does not affect the oscillation frequency because it was compensated by initial stretch of this string. And now when it's both masses oscillate, the midpoint of this string is not moving. It means that we can think about this oscillation as a simultaneous oscillation of two masses relative to this midpoint. It means that one mass oscillates on half of spring, which has effective spring constant 2k. So it means that solution for period will be 2 pi multiplied by square root from m over 2k, or pi multiplied by square root from 2m over k, which is answer B, and that was solution for problem number 10. Problem number 11. An escalator can carry passengers up a vertical distance of 10 meters in 30 seconds. A mischievous person of mass 50 kg walks down the up escalator so that they stay in place with respect to the building. If the child does this for 30 seconds, the total work the child performs on the escalator in the frame of the building is next one. Solution for problem number 11. The average power is F average multiplied by Vy. where F average equal negative mg is the average force exerted by the child on the escalator, and Vy is the vertical velocity of the point of contact. Other words, one or both of the child's shoes when they are touching the escalator. This velocity is precisely the speed of the escalator, 10 over 30 meters per second. The result is this one. Notice that the work done by the child on the escalator is the negative of the work done by escalator on the child, which has the same value mgh as it would have if the child had remained stationary. So that was answer B, and that was a solution for problem number 11. Задача номер 12. A platform just out horizontally from the edge of the building. If the platform is modeled as a uniform metal rod, which one of the following statements about the tensile and the compressive stress is correct? Solution for problem number 12. There must be tensive and compressive forces at the top and the bottom of the rod respectively to balance the torque on the rod from gravity. Ultimately, these forces come from the wall the rod is attached to. That's answer C. There is a horizontal tension in the top of the rod and the compression in the bottom. And that was a solution for problem number 12. Problem number 13. A uniform disk of mass m and radius r is attached at its edge to a flexible pivot on the ceiling. It is given a small displacement perpendicular to the plane of the disk, so that it begins to oscillate perpendicular to the plane of the disk. What is the period of oscillation? The moment of inertia of a disk about the axis going through its center and perpendicular to the plane is I disk equal 1/2 mr square. Solution for problem number 13. If we orient this disk in the direction of perpendicular to plane of disk as axis z, so it means that IZ through the center of disk will be 1/2 mr square. Due to perpendicular axis theorem, we have IZ equal IX plus IY, where IX and IY are moment of inertia around axis of rotation in the plane of disk, which is going through center of disk. And due to symmetry, Ix equal Iy equal 1/4 mr square. Now, due to parallel axis theorem, we have moment of inertia of disk through the edge of this disk, as on the picture, equal 5/4 mr square. And now we can make equation for small oscillation. If we make a small displacement for angle theta, we have torque created by a force of gravity equal negative mgr sine theta, or for small theta that will be negative mgr theta. And now we can write equation that I alpha equal tau, and finally we have angular acceleration proportional to angular displacement with negative sign. It means that this equation describes small oscillations, where this coefficient, that's omega square. We have angular frequency equal this expression, and finally period equal to I multiplied by square root from 5r over g, which is answer B, and that was solution for problem number 13. Problem number 14. A large block of mass 5 kg is moving to the right at a velocity of 10 meters per second. Spaced out every meter are smaller, initially stationary block of mass 1 kg. All collisions are perfectly inelastic. Neglecting friction, how far will the large block travel before its velocity has decreased to below 3 meters per second? Solution for problem number 14. Here we have momentum conservation. It means that full momentum equal to mass of the large block multiplied by its initial speed, which is 50 kg multiplied by meter per second. It means that total momentum is conserved. It means that it's equal to m2 v2, where v2 equal 3 meters per second. It means that m2 equal 16.7 kg. Finally, we see that when we have mass of small blocks is 12 kilograms, our big block speed became first time below 3 meters per second. It means that answer is 12 meters, which is the answer C, and that was solution for problem number 14. Problem number 15. In the device shown, blocks of various masses are placed on a pistons so that the device is in equilibrium. The fluid in the drawing is to scale. There are valves that are both initially open at locations A and B. One of valves is closed and the system is allowed to come to equilibrium. How will this affect the height of the mass m2? Solution for problem number 15. The gauge pressure of the water directly on the block m1 is must be m1g over a1, where a1 is the cross-sectional area of the tube containing block m1. The pressure in the horizontal section of the tube is therefore rho gh plus m1g over a1. But by the same reasoning, the pressure is also rho gh plus m2g over a2 and rho gh plus m3g over a3. Now we conclude that m1g over a1 equal m2g over a2 equal m3g over a3. This is the condition for equilibrium in the device. Now, if we close valve A, the condition for equilibrium in the right two tubes is m2g over a2 equal m3g over a3, which is already met. So these tubes remain in equilibrium. The same applies to valve B. In other words, the pressure is the same to the left and right of the valve. So closing the valve doesn't affect the equilibrium. So it means that right answer is A. Closing either valve will have no effect on the height of M2. That was a solution for problem number 15. Problems number 16 and 17. The following information is relevant to problems 16 and 17. A mass big M sits on top of a vertical spring of a spring constant K in equilibrium. A mass small m is held a height h above it. The mass big M is then pushed downward by distance dx, and both masses are released from rest simultaneously. For what value of h will the two masses first collide when big M first return to its equilibrium position? Solution for problem number 16. First, let's write the equation for time to move for big mass M from bottom part to equilibrium. That will be a quarter of full period, which is pi over 2 multiplied by square root from big M over G. Second, this time equal time to fall down for small mass for distance h. That will be square root from 2h over g. And now we just need to equalize this two times for two masses to meet in equilibrium position. That will be this equation, and from here we can find what is height h. That is pi square big mg over 8k, which is answer D, and that was solution for problem number 16. Problem number 17. Assume that h takes the value found in the previous question and that the collision between the two masses is perfectly elastic. For what value of dx will m small rebound to a maximum height that is exactly equal to its original height? Solution for problem number 17. For small mass m to rebound to the same height, it must go after collision with the same speed that it was right before collision. It means that two masses must collide with the same momentum to get the same speed with the opposite directions. So it means that we have equation m small multiplied by vm small, which is speed of small mass right before collision. That's equal to m big multiplied by vm big, where vm big is speed of big mass right before collision. Both velocities we can find from energy conservation. For big mass we have potential energy for spring must be equal to kinetic energy for big mass, so that will be this equation, and from here we can find what is V big M. That's dx multiplied by square root from k over big M. For small mass we can just count what is the speed of this mass after free fall for distance h, which we just counted in previous problem. That was this expression, and now we can count what is speed for this small mass. That is this equation. And now we can put in the first equation our expressions for these two velocities. That will be this equation. And finally from here we can find what is dx. That will be p small m g over 2k, which is answer E, and that was solution for problem number 17. Problem number 18. An extendable arm is made from rigid beams free to pivot around the dots shown. Spring 1 with the equilibrium length L1 is attached between points A and C, while spring 2 with the equilibrium length L2 is attached between B and D. The system is allowed to come to equilibrium. In equilibrium, what is the ratio of the tension in spring 1 to the tension in spring 2? Solution for problem number 18. Let's write expression for full potential energy of this system. Suppose that first spring has spring constant K1, second spring has spring constant K2, and the distance in equilibrium position between neighbor points like B and C equal x. So it means that total potential energy will be this expression. To find where is the minimum for this potential energy, we need to take first derivative by x, and that will be this equation. Here we have L minus 3x, that's extension for the first spring, and L2 minus 2x, it's extension for the second spring from equilibrium, but K1 multiplied by extension, that's a tension in the first spring, and K2 multiplied by extension, that's a tension in the second spring. So finally we have 3T1 plus 2T2 equals 0, and T1 over T2 equal negative 2/3. That's answer A, and it was solution for problem number 18. Problem number 19. Consider an axially symmetric object that experiences no external forces and initially rotates about its symmetry axis. The object then changes its shape while remaining axially symmetric. Afterward, it is found that its moment of inertia about the symmetry axis has increased. How have its kinetic energy T and the angular velocity omega changed? Solution for problem number 19. Let's write expressions for angular momentum and kinetic energy. Angular momentum L equal moment of inertia multiplied by omega. And the angular momentum is conserved. It means that L is constant, and if we will increase moment of inertia, I, omega must decrease. And also kinetic energy equal 1/2 I omega square. Or we can rewrite it in form of 1/2 L square over I. L is constant, so it means that if I is increased, kinetic energy decreased. And the total answer is A. T has decreased and omega has decreased. That was a solution for problem number 19. Problem number 20. A well-calibrated scale reads 0 when nothing is placed on it. When a deflated balloon is placed on the scale, it reads m small g. When a non-airtight box is placed on the scale, it reads big mg, where big M greater than small m. The balloon is inflated with helium so that it floats upward in air. The balloon is placed in the box, and the box is placed on the scale. If the scale reads W, which of the following is true? Solution for problem number 20. Consider the forces on the box. Before the balloon is in the box, the weight of the box, the buoyant force on the box due to the atmosphere, and the normal force from the scale all balance, and the normal forces big mg. When the balloon is placed in, the only change in the forces on the box is an upward force as the balloon pushes up on the top of the box. Thus, the answer must be less than big mg. However, we don't know whether it is larger or smaller than big M minus small m multiplied by g, because this depends on how buoyant the balloon is, so there is not enough information to decide. And this is answer E. None of the above are necessarily true. And that was solution for problem number 20. Problem number 21. A person stands on the seat of a swing and squats down, so that the distance between their center of mass, cm, and the swing's pivot is L. As the swing gets to the lowest point, the speed of their center of mass is v, At this moment they quickly stand up and thus decrease the distance from the center of mass to the swing's pivot to L prime. Immediately after they finish standing up, the center of mass speed is v prime. Which of the following statements is correct? You might neglect friction, the change in the moment of inertia of the person about the center of mass, and the time take to stand up. Solution for problem number 21. Because the person is doing work to stand up, the energy is not conserved in this problem. Instead, the angular momentum about the swing pivot is conserved, since there is no net torque. The angular momentum about the person's center of mass is mvl, while squatting and mv prime l prime after they stand up. The linear momentum is not conserved because the internal forces in the swing give the person an impulse as they stand up. And due to angular momentum conservation, we have this relation, and from here correct answer is C. VL equal V prime L prime. That was a solution for problem number 21. Problem number 22. A point mass M sits on a long block, also of mass M, which rests on the floor. The coefficient of static and kinetic friction between the mass and the block is mu, and the coefficient of static and kinetic friction between the block and the floor is mu over 3. An impulse given a horizontal momentum P to the point mass. After a long time, how far has the point mass moved relative to the block? Assume the mass does not fall off the block. Solution for problem number 22. First, let's find what is initial velocity of the first block after it getting impulse P. That will be V0 equal P over M. Second, let's find what is the acceleration of the point mass. That will be mass multiplied by A1 equal negative mu mg, which is force of friction, or acceleration A1 equal negative mu g. Second, let's find what is the acceleration of the block on the floor. This we can find from equation ma2 equal mu mg, which is the force of friction between point mass and the block, and minus 2/3 mu mg, which is a force of friction between block and floor. So from here we can find that A2 equal 1/3 mu g. Now we can find what is total relative acceleration of the point mass compared to the block. That will be A1 minus A2, which is negative 4/3 mu g. And finally we can find what is total distance which point mass cover on the block. That will be 0, which is final speed square, minus v0 square, which is initial speed over 2 relative accelerations, and that will be 3 pi square over 8 m square mu g. We can mention that till point mass move compared to the block will always move because total force is positive, which apply to the block. So it means that we can count what is the total relative distance which point mass covered on the block. That will be v square over 2a. And this is answer A. That was solution for problem number 22. Problem number 23. Assume that the drag force for a fish in water depends only on the typical length scale of the fish r, its velocity v, and the density of water ρ. A puffer fish is about 10 centimeters in length and swims at about 5 meters per second. How fast does a clownfish about 1 centimeter in length need to swim such that it experiences the same drag force as the puffer fish? Solution for problem number 23. Here we can use a dimensional analysis. We have that drag force depends only from length, speed, and density of water. So we can write proportion. That drag force proportional to this expression. Here we need to find what are our coefficients A, B, and C. Now we can use dimensions for all these variables. So we have this expression. And now we just need to equalize powers on the left and on the right for the same dimensions. So for mass we have 1 equals C. For time we have -2 equal -b. And for length we have 1 equal A plus B minus 3C. So it means that powers have these numbers. So it means that we have drag force proportional to length square, speed square, and water density power 1. Water density is the same for both fish, and if we decrease length 10 times, we have to increase speed 10 times. And the final solution is 50 meters per second, which is answer C, and that was solution for problem number 23. Problem number 24. 3 boxes A, B, and C lie along a straight line on a horizontal frictionless surface as shown. Box A is initially moving to the right with the speed v, while the other 2 boxes are initially at rest. If all collisions are elastic and the masses of the boxes can be chosen freely, which of the following is closest to the maximum possible final speed of box C? Solution for problem number 24. We can write equation for the speed of block B after collision. For absolutely elastic collision we have this formula, which is almost equal to 2v for mass ma much greater than mass mb. For the same reason we can say that for mass mb much greater than mass mc, we have to multiply this speed by 2, which have maximum speed 4v. And that's answer D, and that was solution for problem number 24. Problem number 25. If a certain radioactive decay process happens n times per hour on average, then in any given hour, one expects to observe n decays with an uncertainty of square root from n. Each hour can be assumed independent of the previous one, and n can be assumed constant over time. How many hours do you need to conduct the observation so that you can determine n within an uncertainty of 1%? Solution for problem number 25. Let the number of hours we observe be h. Then the number of decays observed will be on average hn. The standard deviation in the number of decays observed in an hour is square root from n. Each hour is independent of the ones before it. When we add h independent samples of random variables, the sum has standard deviation of square root from h multiplied by sigma, with the sigma the standard deviation of the underlying distribution. So in our case, we will observe nh decays, and the standard deviation in the number of decays observed is square root from hn. So our estimate for n will be nh plus minus square root from hn. In our case, we have deviation is 1% from total number of decays. So it means that square root from hn equal 0.01 hn. And from here we can find that hn equal 10 power 4 and the h equal 10 over 4 over n. This is answer D, and that was a solution for problem number 25.